Hello again. In the previous lesson, we introduced systems of equations, augmented matrix, and row operations. In this lesson, we'll perform matrix operations and an inverse matrix to solve a system. So here are the quick rules. You can pause the video and read them. Let's go ahead and begin. So example number one, we have essentially a 2 by 2. All right. So we're going to let A equal 2, -1, 3, 4. Okay. And then we're going to let B equal 5, 2, -1, 6. Okay. So notice this is being the top row, this is being the bottom row. And then 2 and 3 represent the column. Then -1 and 4 represent the column of A. Okay. So that's the way we have to look at it. Rows, columns. Rows are, rows are horizontal, columns are vertical. And so what we want to do is we want to find A plus B and A minus B. So in order to find A plus B, what we would essentially do is add the terms together. Okay. So the first one would be 2 plus 5. Then we would have 3 plus -1. Okay. So again, 2 plus 5, 3 plus -1. And then we would do -1 plus 2. And then 4 plus 6. So the final result for A plus B would be 7. 2 plus 1, or excuse me, 2 plus 5 is 7. -1 plus 2 would be +1. And then 3 plus -1 would be +2. And then this would be 10. Okay. So A plus B is 7, 1, and 2, 10. Now let's do A minus B. All right. A minus B would be 2 minus 5. 3 minus a -1. Okay, make sure you're very careful with the double negatives here. And we have -1 minus 2. And then we have 4 minus 6. So the final result for this would be 2 minus 5 is -3. -1 minus a 2 is also -3. 3, this will be opposites, which is addition. 3 plus 1 is going to give me 4. And then 4 minus 2 is going to, 4 minus 6 is going to give me a -2. Okay, just make sure you're careful with this one. And essentially, this completes the answer to number 1. All right, let's continue. Example number 2. So we have letting A equal this and letting B equal this, and then we're gonna have to find the multiplication of this. So this works different from addition, whereas addition you simply add each individual one to each individual one. So first of all, I'm gonna let A equal 1, 3, 2, -1. Okay, so this is a 2 by 2 as well. I'm going to let B equal 4, 0, 5, 2. Okay, and we're going to multiply them. Now, in order to find A times B, both matrices essentially are 2 by 2, so it makes this very easy. The number of columns in A equal the number of columns of B. So what this is saying is that this is clearly defined. Okay, so A times B is defined and will be a 2 by 2. Okay, A is 2 by 2, B is 2 by 2, so um therefore A times B is 2 by 2. Right, so this is 2 by 2, this is 2 by 2, so therefore when you combine them it will be 2 by 2. So in order to do this for the upper left entry, we would simply multiply the row 1 of A by the column 1 of B. Right, so row 1 of A by the column of B. So the way this would look is we'd have 1 times 4 plus 3 times 5. And again, the row of 1, 3 by the column 4, 5. And then we would do 1 by 0 plus 3 by 2. Okay. So again, 1, 3, 1, 3, column 4, 5. 1, 3, column 0, 2. Okay. Then we would compute. So 4 plus 15 would give us 19. 0 plus 6 would give us 6. And then we would do the same thing for this row. Row, column, row, column. All right. That'd be 2, 4 plus -1, 5. Okay. So again, 2, 4, 5. Okay. Then we would do, let's see, as a matter of fact, I'll just go ahead and compute this. So this would be 8, and then -5, that would be 3. All right. And then we would do the bottom, which is 2, 0 plus -1 times 2. Okay. So again, this right here by the second row, all right, or the second column, excuse me, which would result in -2. So AB, or A times B, is a 2 by 2, which is 19, 6, 3, -2, right? And that's the final answer. Again, matrix multiplication is always row by column, right? Do not multiply the entries in the same position as we did before with addition, right? All right, pause and try this problem down here. Okay, so for this problem, we need to start with the dimensions of A, okay? A has 2 rows and 3 columns. So A is 2 by 3, right? 2 rows and 3 columns. 2 rows, 3 columns. You always want to look at it from that perspective. So in multiplication, it's row by column, right? Row by column. So it's a 2 by 3, right? Matrix B has 3 rows and 2 columns, okay? 3 rows and 2 columns, right? 2 rows and 3 columns, okay? I didn't put my N down here, okay? So B is equal to 3 rows, 2 columns, okay? So therefore, if we said, it says state the dimensions of AB and BA, so AB, or A times B, would essentially be 2 times 3 and 3 times 2, okay? So if we, essentially what we can look at is these inside terms. The inside dimensions are both 3. So this says is defined. Okay, when the inside dimensions are the same, that means it is defined. And then the outside answer, or the outside dimensions, give the dimensions of the answer, okay? So is defined, and 2 tells us the dimensions, okay? So again, A times B, or AB, is defined, and AB would be 2 by 2, right? Now let's look at BA, or B times A. So B times A would be 3 by 2 and 2 by 3. Okay, so again, looking here, we see that the 2 internal terms are the same, so that it is defined here. And the 3's tell us that this will be a 3 by 3. Okay, so the dimensions would be a 3 by 3. Okay, so the final answers are AB is defined, and it would be 2 by 2. BA is defined, and the dimensions would be 3 by 3. Even though the products are defined, they do not have the same dimensions, clearly, right? So therefore, they won't be equal. They cannot be equal. All right, let's move on to the back. Here we have an inverse. So it says find the inverse of A for A equals 2 over 1 as a row, and then the bottom row is 5 over 3. Verify by multiplying. All right. So the inverse of A is what we're looking for. So we essentially have A equals 2, 5, 1, 3. Okay, so that's what we're working with, and we're looking for the inverse. Okay. So for any 2 by 2, any 2 by 2 would essentially be A, B, C. Okay. And then we have what is called the inverse formula. The inverse formula is the inverse of A equals 1 divided by the determinant, which is AD minus BC. And then that is multiplied by matrix of D negative C negative B A. Okay. So finding the determinant is very simple. I'm going to set it up. Determinant of A in this particular problem, because we're looking for the determinant of A in this. It would be D minus BC. A is 2, D is 3, minus B is 1, so minus 1, and then C would be 5. Okay, so those terms come directly from here, right? So A would be 2, B would be 1, D would be 3, and C would be 5. Okay, so just be very careful making sure that those things correspond. Then we have 6 minus 5 equals 1. Okay, so the determinant, as you can see, exists because remember, you can't have if it becomes 0, then the determinant doesn't exist, right? Or this inverse doesn't exist. That's essentially what it says. Again, so the determinant is not 0, so the inverse actually exists. So what we can do is we can say, okay, we know that it exists. So this would be 1 over 1, right? So 1, and then we found this right here, the determinant, which is also 1. Then we would multiply that by 3, negative 1, negative 5, and A is 2. Okay. So all I did was D is 3. That's where all these numbers come from the inverse. Okay. And these are the inverses, right? So don't get that confused. Okay. So I'm just solving straight across. All right. And then it simplifies to 1 divided by 1 is just 1. So this would be 3, negative 1, negative 5, and 2. Now we verify by multiplying A times the inverse of negative 1. So that's essentially A times the inverse of, or excuse me, A times the inverse. And then we would multiply 2, 1, 5, 3, right? 2, 1, 5, 3. And then we would multiply that by 3, negative 1, negative 5, and 2. Okay, because it says verify by multiplying A times the inverse over here. Then we would essentially calculate each entry. So we have the upper row, that would be 2 times 3 plus 1 times negative 5. So that would be, let's see, I want to run out of room over here. So that'd be 6 plus -5, or 6 minus 5, which is simply 1. Okay. So again, remember when you're multiplying, you're doing row to column. Okay. So row times column, row times column. The next would be 2, -1 plus 1 times 2, which is -2 plus a +2, or 0. Then the lower would be 5 and 3 plus 3 and -5. That's 15 plus, or 15 plus -15, or 15 minus 15, which is 0. And then the lower right, which is 5, -1 plus 3, 2. So that's -5 plus 6, which is a +1. Okay. So essentially, what this is 1, 0, 0, 1. Okay. 1, 0, 0, 1. So the product is the identity matrix. Okay. This is the identity matrix here. And that confirms that the inverse is indeed correct. All right, let's continue. Example number 4, it says write the system here and here as ax equals b, then use the inverse to solve for x and y. So we have x plus 2y equals 7. We have 3x minus y equals 5. And we have to write them as ax equals b. Okay. And then we're going to use the inverse of a to solve for x and y. All right. The coefficient matrix is formed by the coefficients of x and y. So a is equal to 1, 2, 3, and -1. Right. So 1, 2, 3, and -1. The variable matrix is x, which is essentially x, y. Okay. So that's what that stands for. This variable here stands for the variable matrix. Okay. So x equals xy, because those are the variables that we're dealing with here. The constant matrix is b, which is 7, 5, right? 7, 5. That would be the b, which is established here. Okay. So essentially, if we're writing a variable x equals b, to solve for x, we would multiply both sides by the inverse of a. Okay. So what we would do is essentially x equals inverse of a of b. Then we need to find the determinant. So the determinant of a is equal to 1, -1 minus 2 and 3. Okay. So 1 minus -1, or excuse me, 1 multiplied by -1 minus 2 multiplied by 3. This would be essentially -7. The determinant of a is -7. So the determinant is not 0, so the inverse definitely exists. And so we would use a 2 by 2, the 2 by 2 inverse formula. So we know from the previous problem, that would be, in this case, 1 over the determinant, which we found out was 7, or -7. And then we would multiply that by -1, -2, -3, and 1. Again, this is going off of the inverse formula up here. Okay. Okay, so you'll have to use that side by side when you're working these problems out if you don't know it by memory. Okay, so we can distribute the negative 1/7 to each term, right? So by distributing the negative 1/7 to each term, we end up with negative 1/7 times negative 1, which is going to be 1/7. And then just computing the rest, 2/7 positive, 3/7 positive, and negative 1/7. Okay, again, and that's just me distributing this negative 1/7 to each term. All right. Now we need to multiply the inverse of A by B. So what that would look like is, I'm running out of space here. That'd be 1/7, 3/7, 2/7, negative 1/7 times B, which is 7, 5. So the first entry gives us X, right? So X equals 1/7 times 7 plus 2/7 times 5. 1/7 times 7 would just be 1. 1 plus 10 over 7. Let me see, 1 plus 10 over 7. That'd be 7 over 7. So that'd be 17 over 7. So that's 17 over 7. All right. And then the second entry gives us Y. So Y equals 3/7 multiplied by 5, or excuse me, multiplied by 7 first, plus negative 1/7 multiplied by 5. Okay, so this will obviously be negative. So this will be 3 times 7 is 21. 21 divided by 7 would be 3. Then this would be a negative 5 over 7. The denominators would have to be the same. So that'd be 3 times 7. That's 21. 21 minus 5 would be 16. So that'd be 16. Y is equal to 16 over 7. So the solution is X is equal to 17 over 7, and Y is equal to 16 over 7. Okay. Very lengthy problem. A common mistake. As a matter of fact, let me see. I could check this. We could check this to see, the answer to this. We could essentially say, uh, let's see. We could really just check the first one if we wanted to, x plus 2y, and then substitute 17 over 7 and, plus 2 times 16 over 7, and then combine them, and then the result obviously would be 7, because 17 over 7 times 2, excuse me, plus 2. As a matter of fact, I'll just do that real quick so I can help you visualize it. So x is 17 over 7, so that's 17 over 7, and then I'm going to be multiplying 2 by 16 over 7. So 2 times 16 would be 32 over 7. Well, 17 and 32 make 49. 49 over 7 is equal to 7. So this checks out. Okay. And then you can check the other ones if you like. All right. So the common mistake is a student assumes AB equals BA for every pair of matrices. Explain the error and use a small example to show why order matters. So ordinary number multiplication is commutative. Okay. So in other words, for example, um, 3 times 5 is equal to 5 times 3. So if you switch numbers up in multiplication, they're going to give you the same result. But multiplication is generally not commutative. Okay. So what that means is AB is usually not equal to BA, right? And this is with respect to matrices. Okay. Matrix multiplication is generally not commutative. Okay. But in a regular sentence, this is, obviously this would be 15 equal 15. That would check out. But when it comes to matrix, it's different, right? So if A is equal to 1, 1, 0, 1, and B is equal to 1, 0, 1, 1, right? Let's first calculate AB, right? So AB is equal to 2, 1, 1, 1. Okay. And again, if we're multiplying, we go row, column. Okay. Row, column, row, column. All right. That's how I got that very quickly. And then if we're doing BA multiplying, we would end up with 1, 1, 1, 2. Okay. So look at the products. The products are different. So AB is not equivalent to BA with respect to matrices. But if we were doing just simple, multiplication in a line, then obviously that is true. But commutative, it's not true with respect to matrices, generally speaking. All right, so let's review. Addition and subtraction require equal dimensions, which is what we saw here. They require equal dimensions. Matrix multiplication uses row by column. Okay, so you go row by column, row again by column, then row, column. Okay, that's how you calculate multiplication. It's also important to know a 2 by 2 inverse exists only, and I'll write this up here. A 2 by 2 exists only when AD minus BC is not equal to 0. And then to solve for a variable x equals b, what you need to do is x equals the inverse times b. Okay, so to solve for this, you have to use this. Okay. All right. All right, that concludes this presentation. And this presentation is video 17, part 2, matrix operations in inverse. And I hope to see you in the next one.